Welcome everybody to the CIAMB UFC Seminar Global Rivers in the Anthropocene. Please remember that you can write your questions in the chat and we will transfer the questions to the speaker. Also, if you wish to identify yourself, please write your name in the chat. We don't have a direct access to the list of participants because we are using the YouTube channel of the Federal University of Goiás. So feel free to do that. Well, today's speaker is Dr. Lucas Dominguez Ruben. Lucas is a PhD in engineering, specialized in water resources. He's a professor of the Faculty of Engineering and Water Resources Science, Fitch, National University of Litoral, Argentina. He's acting as an associate professor of hydraulic in the Water Resource Engineering program at the same university. He's also a researcher of the National Council of Scientific and Technical Research, CONICET, of Argentina. His field of research focuses on the geomorphological characterization of large fluvial systems, encompassing meandering channels, bifurcations, and fluvial deltas. His study topic is the mathematical modeling, hydrosedimentology, morphodynamic, and sediment transport using 2D and 3D models. He's a specialist in the use of geophysical instruments such as ADCPs. Lucas has developed several specialized softwares in fluvial hydraulic, and one of them, the Acoustic Sediment Estimation Toolbox, asset, and the Meander Statistic Toolbook, MS-TAT. These tools are available for use and collaboration. In case you want to make use of this stuff, please contact Lucas. Well, Lucas, that's all I have to say now. Thank you for participating and for accepting our invitation to the Global Rivers in the Anthropocene. It's an honor for us to have you. You are a collaborator in our institute, in these days also acting like a visiting researcher of our program. So welcome, Lucas. The stage is yours.
Okay. Well, thanks. Today I will talk about the complement of the acoustic sensing or the acoustic sediment and can improve the numerical modeling and transforming the sediment studies. So we talk about from the measurements, from the field work to go to the numerical model and improve the numerical model and better calibration and better the results of the numerical model. First, I will talk about the research group. I'm from Argentina. I work in CEFAL. CEFAL is a group of hydro environment of Argentina. And the results of this presentation is in collaboration with another members. And I am member of TELA. TELA is a group of Latin American in experimental hydrometrics. So we have a group of experts that have different topics, and we do talks, we do divulgation, we do different manuals to improve the measurements using acoustics equipment. Well, again, the idea of today is pass from the acoustic survey, particular in large rivers, and improve the hydrosedimentology numerical model. This is a numerical model in the Paraná River, in particular in Chapeton. So we start before with how can obtain the measurement data, how can convert the measurement data to concentration, to suspended sediment concentration, and how can improve the results of the numerical model. First, I will talk my study site. This is the Paraná River. Okay, well, the Paraná River is a large river. Edgardo studied a lot of Paraná River, and this is the main characteristic of Paraná Rivers. It's a system. It's a big system that have a large valley width, 15 kilometers, have a ratio of width depth ratio of 100, have a maximum flow discharge of 40,000 meters cubic per second, and an average free slope from 2 to 5 centimeters per kilometer. It's a alluvial river, it's an branching river, and have a sediment behavior of 95 million tons per year. So move a lot of sediment. Of total sediment transport, the portion of wash load and suspended bed sediment is 67 correspond to wash load. The fine fraction is silt and clay. 21 is suspended bed material, and only 2% is bed load. The behavior of the Paraná of the sediment transferring is really complex. An important river in this environment is the Bermejo. Bermejo is a tributary river that have a mouth in the Paraguay, next the Paraná, and next along the Paraná River, transfer of the secondary system. The secondary systems live in the same time with the main of Paraná River, and allow the transfers of water and sediments to Valley of Paraná. So it's an important participation in this building of the environment of the secondary system, no? The Paraná River have a behavior that have a pattern with high wash load from February to June, and have in the same times the tributary sands during the same months from February to June. So the participation of the secondary river is really important. Again, like a Colastina River. Colastina River connect the main channel to the secondary along the alluvial valley, and close to the Santa Fe city, close to the big city of Argentina and Paraná city. So this is a general behavior of the Paraná River, and we start with the motivation that move this research. So this is a conceptual graph of USGS that we can see the water flow discharge and sediment concentration. Normally the water discharge or the levels, we can measurement every day or every 15 minutes. We have a high resolution, high temporal resolution. So we can see the blue lines here, and we have in scatter and red scatter the concentrations behavior alone in the same time, no? But the problem is that we measurement the concentration, we capture only some spines. So we don't have capture all the behavior of the concentration, because it's really difficult go to measurements suspended sediment or bed load sediment and have a behavior or the change in the river. And it's more complex when we have a tributary that don't match with the hydrologic behavior of the river. So we know that conventional measurements or techniques, that you go to the field work, you take a sampler and analyze in the laboratory, but we have a lot of problems. We have difficult to apply. These techniques require different specialists and equipments, training person, and we have different challenges in large and remote rivers, no? The sediment time is long sampling times. Collecting represent sometimes more time to take the sample, and more if we use the isokinetic sampler, is really stronger. We need to download the sampler and upload the sampler, take the sampler, and a lot of things. And we have a limited spatial and temporal resolution. In a conventional method, you should provide a discrete measurements at a specific location in times. I will talk about this. So this results in limited understanding despite numerous contributions. No? The new technologies, the acoustic technologies, allow improve this. No, we can improve the velocity and the flow structure. We can describe better the flow structure in large river. And the idea of this part of the presentation is talk about how can convert the acoustic signal obtained particularly in TRD ADCP in sandy bed fluvial system to estimate the suspended sediment concentration and transport. So I present one only slide of this. This is the acoustic theory. No? We have in the up of the slide, we see the complete expressions or equation. We have in the left hand the backscattering representation, and we have in the right hand different parameters that describe the acoustics effects and influence along the backscattering. If we see the hand signs, we have a representation of the attenuation. This term is really important because in the rivers that have a fine fraction and coarse fractions, normally the backscattering is dominated by a coarse fraction, but the attenuation is dominated by the fine fraction. So both terms combine, and in different situations depends of the rivers, but in this expression we can obtain the concentration of the river. We input the signal, and we input a lot of things like transmission power, transmission length, and other acoustic variables. But we have another problems. We have a particular problems related the acoustic noise. The acoustic noise is the IR term that represents the noise of the environment and the instrument. So we need to calibrate this parameter, to apply this equation. If we simplify this equation, we can solve this and obtain this expression that only input the sound fractions represented by subscript 2, and we incorporate in the ST term a lot of parameters that have in the first equation. So we can obtain the concentration first, calibrating the principal equation, and then input in the second simplified equation. This resolution you can use using the acoustic sediment estimation toolbox. This toolbox estimates the suspended sediment transport from the discharge measurements. Only work for the single frequency ADCP from Teledyne RDI instruments, both frequencies, 600 and 1,200 kilohertz. Sorry. You can download the code. It's a free software, and you can download the paper that have the acoustic theory, and you can download in different forms, in source codes or in executive format of the code. And you have a blog that have a tutorial and other things. So we have before a disclaimer for implementation. This software can apply in different frequencies, different equipment, but we need a sedimentological characteristics of fluvial system, like a bimodal system, sandy bed, no flux, and no organic matter in importer taxes. No, this software was applied in different rivers with good results, like Paraná, Missouri River, Sacramento, San Joseph, and Uruguay River. We explain very fast how work this software. This software have two models, two principal models. No, the first model is a calibration model that we obtain the IR parameter, the noise of environments and equipment, and we have an implementation model. For the calibration model, well, we need to go to the field work. We need to go with IDCP, ecosonder, notebooks, and GPS corrections in field trip. And we take the sampler, we see the sampler, we pass with the laboratory sampler, and we obtain the concentration and diameter. So in this presentation, I will talk about the 5 locations along the Paraná River. So first, to calibration, we need to determine the vertical across the section. We need to do a measurement of the cross section that we select to measurements. We need to apply the equal discharge increment method. We can download the software, ADI software, and we can obtain the 5 verticals. Well, the 5 verticals we can obtain with GPS, with the latitude and longitude position. When we have these 5 positions, we go with the ADCP, for example, the vertical 3, and we put on the ADCP, take a measurement, and then at the same time we download for example, the sampler USP 61 in different points of the verticals, 20%, 40%, 0.5%, 60%, 8%. We take the sample, punctual sample, and then we analyze in the laboratory, and we obtain the concentration of both fractions, fine and coarse, and we obtain the diameter of both fractions too, of fine and coarse fraction. We can change this method using a list, because we can obtain in the fieldwork the concentration and diameter at the same time, no? Well, the calibration, we input the acoustic signal and we input the sedimentology data, and we obtain the parameter of the noise. So if it's okay, we have a good correlation, and you obtain the calibration parameter. So we finish the calibration, and we can go to the implementation of the software. We can do a calibration, and we can implement in past surveys. So it's an improvement of the software. We can calibrate in the reach, in particular reach of the river, and we can apply after measurements or before measurements. To apply, we need to input the ADCP data, the PDO, ASCII, or .mat from the BMT, or another software of the USGS, and we input the fine sediment diameter, coarse sediment diameter is a mean diameter of a cross section, and fine concentration that we take the day of the measurement. We can do different extrapolation methods, and we obtain the measurements of the total transport, surface transport, bottom transport of the sand load and wash load. The software used on the measurement zones different extrapolations, close to the surface, close to the margin, and close to the river bed. The software can select the user's different methods of extrapolation, 3-point lines, log profile or log of wall for velocity, and we can use 3-point line and rose profiles to extrapolate close to the surface and close to the bottom using the measurements, the data measurement. So we can check the different method of extrapolation and implement this. Now, additionally, we can use the extrapolation close to the margin. It's similar that use the Wind River software. We can use, depending on the shape of the margin, triangular or rectangular, we can extrapolate the constant, the sediment transport close to the margins. So with this, the results that implement the asset software, and in the different cross sections, this first part of the table show the measurements, the traditional methods, and this part of the table shows the sediment transport using asset. The more highest difference is than 15% in sediments. It's a good percentage, but we can obtain a mean average of 19% using asset. And how can we can improve the results using the Monte Carlo method. The Monte Carlo method we can implement in asset. We can put a lot of parameters, input parameters, and the deviation, and we can obtain the mean of the sediment transport and the deviation, and we can obtain the percentage that influence that each parameter. So we can see here that the KCR, the noise parameter, have a highest percentage of the total parameter of the calculate of sediment transport. These some conclusions of this part, and we can see in the left part the traditional method with 5 points in each vertical, in 5 verticals, and we have here the use of asset, the result of asset. We have a high spatial and temporal resolution, and we in same time we have a velocity and flow structure, so we can improve the results, combine both results, the flow structure and sediment transport. I think that we have reduced the time of the measurement and if we compare with the traditional or conventional methods. I know that the maximum difference between the traditional and this acoustic method is 50% for all cases of extrapolation. We need continued testing in different fluvial systems. This software, we have incorporated the influence of the suspended particle size distribution and how affect the attenuation of the absorption of signal, and we're working now in converting the code from MATLAB to Python. Well, this is the first part, and we can show some implementation that this improve using numerical model. This is a Paraná River. This is a big diffluent confluence units along the Paraná rivers. So we can see here different bifurcations. This is a multiple bifurcations. And we need to understand here how changing the morphology in different time of this structure, and how can design infrastructure or different protection for the future evolution of this bifurcation, because these bifurcations impact of the Colastina River that we have a lot of infrastructure for the big or large cities in Argentina. So we study this bifurcation in different years, and we study that we have a complex behavior. If we see the bifurcation 1, we see in different years, we can see the fraction of flow discharge, how separate for the west channel and east channel. So we see that while the flow channel go to the west channel, less flow discharge in sediments, the right of the graph, this change. So what happened here? Sometimes we in a lot of numerical approach, the link of the flow discharge and sediment discharge is the same, but this behavior shows difference from the sediment and the flow structure. And if we see the right part of this presentation, here we see the concentration of the sands, and we can see in the first section, in cross-section 1, in the bifurcation head, we can see that the core of maximum concentration is close to the right bank. So this favor to transferring the suspended sediment to the west channel, but not for the east channel that he grow in the time today. So this is one of the implementation of this asset of the acoustic river, and we can see here the flow discharge or specific discharge, and we can see that in black lines that the core is more close to the left, and the core of the maximum concentration is more the right hand, represent this shift between the flow and the suspended sediment. We do a different modeling, and we found another things that we found that like a flow acceleration between two channels, that these form and bars and island. After we do a modeling of during flow simulation, and we can find that if we move off the island, we have different shear velocity that favor the growth of the island in that difference confluence units. This is another example. This is in the meandering river. We found that while the flow structure shifts from one margin to another margin, the core of maximum velocity, the sediment maintains in the center of the river. So this is a problem. The secondary component move from one to another point, the transversal flow of suspended sediment. So this is the results of the measurements. Here we can see the flow structure, and here we can see the suspended sediment, and how it represents in numerical model. We go to the Open Telemac Masquerade, and we use this software. We using different combination of corrections. We incorporate a correction that use this type of conservations. So we run the simulation, we calibrate the velocity, and we obtain this result for 2D modeling, and we obtain that the suspended sediments maintain the center of the river like a measurement say, because if we using the traditionally correction, we obtain that the sediments move with the flow structure, move from one margin to another margin. But in this river, like I showed it, the suspended sediment maintain of the center of the margin, but the velocity move from one to another margin. So, well, we do a 3D modeling, and this is some results from different cross sections. And in black line is the measurements and the different result. We obtain the better results in using Telemac 3D, but it's really cost for numerical modeling. And we incorporate this correction to improve the results, and we reduce notably the numerical time in the numerical time cost using 2D results. This is the last implementation. This is in north of Argentina, and this is a growing series of growings in Mountain River, in the Rio River of Valley, and this is that a structure that contains the margin of the river. So we implement the Telemark River, and we obtain different results that move off the bed of the river, and we compare the results with the numerical simulation, and we obtain good results. And this allow it better the geometrical disposition of geometrical position of the groinings to good better results. Well, I will thanks, obrigado and muchas gracias to my invitation, Professor Edgardo Latruese, and if we have questions, I don't have a problem.
Thank you very much, Lucas, for this very exciting sharing with us. This is very exciting results. It's very important. So we are lucky to have you here. Please remember the public write your questions in the comments so we can answer the questions to the speaker. Please go ahead and write your questions. Do we have some questions? No. One question. Why the history of the 300 kilohertz fall in the equipment of 300 kilohertz? What aspect of the methodology should be taken into account in relation to the 600 or 1200?
Well, we don't difference if we use 600 or 1200 kilohertz. I think that the more difficult of the methodology is have the calibration, because we need to go to the field work, and we need to go to the field, and we need to take a sample, and this is really complex, and it's not easy. But when then implement this code, we can implement in different other situations, and it's really easy, and we have a high resolution and spatial and temporal resolution. I think that's the more important and more difficult part of the implementation is the finish the calibration, no? Because we need a laboratory, we need go to the field trip, take sample.
We have another question here. What's the size of the grid? We explained a little bit. Discharge equivalent, right? For the sample. Right?
How much?
Okay. How do you design it?
How do you design it? Well,
the grid of samples on the time that you get this. Measurement.
Sometimes, yes, we take one sample per each vertical, and the time it's variable, because it's another problem that you take a static, you go out the vessel of using the river, using the boat, and we have movements, but sometimes in the part of the river that has a high velocity, we can maintain quick, and per each sample we have maybe 15 or 10 minutes per each sample, and if we in totally maybe we can, if all the sample is good and we don't have a problem, maybe we need 4 hours to complete the field work for the calibration. No?
Okay. Thank you very much. More questions? I have some. Let's see if we have some questions from the public. I I have some questions. First of all, it's more than a question of observation. So we know that the challenge that these techniques and methods that you develop is because fluid specialists like us have been facing a lot of problems to estimate suspended sand rivers, right?
Yes.
Usually you have, the suspended load all together. In many agencies, we are not separating grain sizes, right? Some people at the USGS, they separate the fractions. In the good part of the agency, they don't separate the fractions, including maybe in our agency. But
Yes.
we get the general value of suspended sediment concentration. Also, another problem is that usually the agency uses water column integrated samples. So they take samples of the full water column, so we average concentration in the whole of the column to estimate the concentration. So all this is offering a total new perspective, right?
Yes.
Kind of revolution for
Yes.
our field.
Yes, I think that's the use of integral sample can describe the behavior of the sands, that we have a high concentration close to the bottom. So, but the use of the punctual is improve the results. You can use, for example, no separate the both fraction, but we can both separate using in laboratory, obtaining the particle size distribution, and we can separate the concentration using post-processing. Yes, it's normally.
We have been talking another meeting that we had with the Russian colleagues, Professor Seychel Chalov from Lomonosov University. They are doing kind of similar kind of studies in big rivers in Siberia. And I say, well, I clap you because you are measuring in the field, you go into the field with all these acoustic equipment, trying to separate the different fractions and how we can really understand this mechanism. Because more and more we have now people using databases.
Yes.
Global databases. So they take suspended sediment concentration values from different agencies. They put all together in the same database, make a unique, only mixture of suspended sediment concentration and can be anything.
Yes.
Right? Can be integrated samples, can be surface samples, can be punctual samples, everything. Right? And after they use the satellite, we got several papers in big journals about that. A global estimation of suspended sediment transport in the rivers across the world. So the last 10 years, 20 years, we have a decline, we have this, we have that. I mean, it's absolutely, in my opinion, good, but totally wrong what they are doing.
Yes, it's not easy. It's not easy to capture the behavior of the sands, particularly the sands, now, because it's really complex.
And think about that, for example, if we take a suspended sediment concentration, river like the Amazon, upper 10 meters, we don't have sand. So I take an average value of the whole water column. I want to take with the signal of the surface of the satellite to say that we are representing the cool water column. And the same other river like you have. Another interesting question I have for you, that you are also a modeler of morphodynamics.
Yes.
Many people have been talking about the influence of sediments on the capacity to produce erosion and to accelerate migration rates, particularly in meandering rivers. We have, for example, Dune and Constantine paper. Okay, well, they use, because in many places we don't have data enough. Okay, just a process of suspended sediment concentration. River with more suspended sediment concentration, they tend to have more lateral migration activity, the river with less suspended sediment concentration. So this will be an influence in shear stress and so on from suspended sediment concentration. After we have, you know very well, Abad and Garcia, the Kinoshita channels and so on, where, okay, the bed load specifically can increase the shear stress.
Yes.
And increment the lateral migration rate, right? This is something that we see with other reason we have explanation for all the very high C. But you are showing now that in many cases we don't have a direct influence on the banks.
Yes, yes.
How you match this kind of issues?
I don't know, but maybe is the behavior here in the Paraná, in this river, is that this is the first measurement that we have a good resolution with suspended sediment transport, no? Maybe in this type of river, we have a main tributary like Bermejo River that he put in the system a lot of sediment transport. And this is the principal river that produce the morphological changes in the Paraná River that maybe in our cases, no? Right? In our cases, the Paraná River, the Bermejo River control this of behaviors of this of pattern in particular. I know that if you don't have maybe a tributary river like a Bermejo, maybe you need a source of sediment. You need the source that move of the river, and maybe you need a source of the bottom, or maybe you need a source of the margin. So maybe in other parts of the world, we can see the behavior like describe dunes or abad, no? From the bottom or from the margin. Yes, yes. For example, the contact with the margin in the Colacine, the meanders create a roughened margin, roughened external margin, and we have a vegetations, and we have a different type of vegetation that control some margins of the river.
No erosion.
No erosion. Yes, and the net flux with the bottom is not important in the Colacine. The sediments, the sands, the behavior of sand is similar that wash low in sometimes that move a lot of kilometers. And maybe one found a low velocity, well, first deposit in the bottom of the river. So
we have, please encourage the public to make questions. It's a good opportunity. Yeah, this another. We have here our colleague Jorge Abad talking about. Lucas will talk. A quick question: is there a way to extract the channel-based sediment transport from the effects from plant migration, especially those on a branching structure? It's roasted here in the screen, so you want to follow up with the question?
Here, in a branching, this?
It says there is a way to extract the channel-based sediment transport from the effect from plant migration. Why can you put the questions on the screen so we can revisit the question in more detail? You can read it now.
No.
Not yet.
No yet.
So I will show you now.
Yeah. So. Yes. I think that. Thanks, Jorge. I think that it's a good opportunity to control the sediment transference from the valley and control the plan for migration. We can see here how. So again, we do a measurement and we take a photograph of that instant that we take a measurement. We can see the average behavior in that cross sections. So we can see there how can migrate or how can I see what is the trapped efficiency that one channel or another channel. So we can see the better condition one channel to another for the suspended sediment, in particular for the wash load and for the sand. And I think that we can see different structures in an branching like I present before. And maybe in the simple approach, like one channel and two bifurcations, don't take account this type of problems, because normally this approach link the hydrodynamic with the sedimentology. So we can see high velocity, high sediment concentrations, suspended sediment concentrations, and in the real measurements, we see that we have a lag or shift between sediment and the flow structure.
Yeah, and by the way, it was depend on always with the different aspect. Right? You have the angle.
Yes.
For example, even Jorge have been looking to that. The depend on how you approach the trend of it's like a trend, right? Particularly
Yes.
low or whatever can follow the couplet from sediment. We know different.
Yes.
From our studies as well in the rivers.
Yes.
You decouple the bedload forms,
Yes.
bed forms, that they are also related, of course, hydrodynamically to the suspended sands transports.
Yes.
And not necessarily is coupled with the, what you say, with the wash load transport.
No.
There is always a tendency to follow these trends. If we move the water toward another direction, not necessarily the trend of bed forms and
not necessarily.
related suspended sand is going to follow this path.
Yes.
Interesting. There's no if we have more questions. Thank you, Jorge, for the question. We don't have more questions. So, Lucas, I want to thank you again for this very nice talk, very important, very interesting.
Thanks for invitation.
Thank you very much to everybody for attending this new seminar. We hope to have you in the next one. Right? We will continue with the full year offering the seminar Global Rivers in the Anthropocene. Thank you very much.